Okay, example 6. The region enclosed by the curves y equals x cubed and x squared is rotated about the line x equals -1. Find the value of the resulting solid. Okay, this time the line x equals -1. So what I would probably do here is probably go x at a 0.5 scale and y at a 0.25 scale. Because again, x equals -1, that means I'm going to be rotating this way. And again, I'm off the axis a little bit, so I want to allow myself a little bit of extra room to be able to do this. So it's the same two graphs we did already, but now we're going into 0.5 scale on the x-axis, so I've got to get rid of the 0.25 and the 0.75 here. You can still graph those if you want to. They're halfway between, but just gives a little less detail maybe. So I got 0, 0, 0.5, 0.125, which will be right here. 0.25, so halfway between 0.0 and 0.25, and then 1, 1. There's my outside piece. And then my other one is 0, 0, 0.5, 0.25, and 1, 1. Actually looks like a straight line even though it's not. Put a little bit of a bend to it.
Shouldn't it go up more? Because your y is at a 0.25 and isn't it 1, 1?
Oh, thank you. That's why it doesn't look right. Thank you, Logan. All right, let's try this again. So, good thing Logan's paying attention better now. 0, 0, and then 1 would be 0.25, 0.5, 0.75, 1 up here.
Wait, what? Oh.
There we go. That's better. So then this and this and that. So there's the other one. All right. So there's our region that we're rotating around the line x equals -1. And if I put in my line x equals -1, which will be right here, there's my axis of rotation. I'm going to rotate that around that, so the reflection is going to be over here. And again, to get the correct reflection, it's just a matter of seeing where the points are and going the same distance away. So 0, 0 is 1 away, so I go 1 away here. 1, 1 is 2 away, so I go 2 away here. And I make the outside and the inside radius happen. Not taking out points for artwork, so you can see that got a little large there, but the whole idea is that we want to be able to see where things are coming from. So looking at this, if I'm drawing in my cross section, all right, so imagining a cross section here, we have an outside and an inside radius circle on a cross section. So again, we're chopping it off somewhere in the middle, so I'm just going to put a cross section right here. There's my outside circle, and here's my inside circle. Well, that's not very good. All right. Pretend that a red circle is a little bit prettier than it actually is, because I don't want to start erasing, because I have to redraw it. Got a little bit messed up there. So my outside circle is blue, my inside circle is red. They're concentric circles. So again, my goal here is to find the radius of these two circles. And the area that we're considering is the area inside the circle. So inside the blue and outside the red. So this area out here. Now, again, what we're looking at is we're looking for things that are always the same, involving the radius and either x or y and the axis rotation. All right, so see if you can buy all this stuff. I'll try and sell you a few things, and I'm going to be completely honest and truthful as I do this, so there's no lies. I don't want to lie about math. This distance here is never going to change. The distance between x equals -1 and the y-axis, which is x equals 0, is always going to be 1 space. That's one of the things you always want to consider. How far is it from the axis of rotation to the x or y axis? Okay. Notice, here's my region. Here's where the radius is going to come from, right? Over here. So I'm worried about from here to here is always going to be 1. Also, this segment here, let me just go with the blue one. That's the radius of the circle right there, right? And finally, from here to here is x. All right? Those are the 3 things we need to consider each time. What's the radius? And either x or y is going to be the distance from the axis to the curve. And how far is it from the axis to the axis? Axis of rotation to the y or x-axis. Those are the 3 things we have to figure out each time. Looking at this picture, this is x, and if we wanted to call this, that's y sub 1, x sub 1, right? The blue is y equals x cubed, and the red is y equals x squared. So we're using subscript 1, subscript 2 to represent these things, right? So that little segment there from here to here is x sub 1, made by the blue curve, which was created by the y equals x cubed. All right? The green is the radius of the circle that we're looking for, and the black is always going to be 1. So again, looking at those 3 pieces, the black, the blue, and the green, the distance from axis of rotation to y-axis, the distance from y-axis to curve, and the actual radius of the circle that we're looking for, those 3 segments are always what we consider. Short plus short equals long is the relationship. Every time it's short plus short equals long. So, short 1 plus short x sub 1 equals long r. The last problem, the radius equaled number minus y, right? Now, number plus x equals the radius. So again, each problem has its own personality. It's up to you to establish that. But you need to find those 3 segment lengths each time. How far is it from axis of rotation to x or y axis? How far is it from x or y axis to curve? And how far is the radius? Short and short make long each time. And that's x sub 1, so that means the same goes for x sub 2, right? So 1 plus x sub 2 also equals r. All right. This is the outside radius. The outside radius came from here. And I need this to be in terms of y, not x. So, if you look at the blue equation, y equals x cubed. If y equals x cubed, that means x equals the cube root of y. And a better way of looking at it is x equals y to the 1/3 power. My circles are positioned this way. They're going to be moving up and down, so I need my integral to be all about y. So I need this radius to be all about y. Right now it's all about x. So 1 plus x sub 1 equals y to the 1/3 power. So this is going to be 1 plus y to the 1/3 power. If we look at the red radius, same structure. Again, if I'm just looking at the red radius, it's only this piece, and the radius is only that piece, right? That's x sub 2, and that's still r sub 2 if you want to call it that. All right. Y equals x squared means that x equals plus or minus the square root of y. But notice we've got the positive square root of y, right? Because x is positive. Negative square root of y will be over there, right? So because our region's right here, we're taking the positive square root of y. And that's the same as y to the 1/2 power. So the inside radius is going to be 1 plus x, which is y to the 1/2 power. That is the biggest challenge, in my opinion, in these problems. What is the radius? Okay, it's a little tricky. You got to get a little creative. Sometimes you have to get equations solved for a different variable in order to get what you're looking for. But once you get those radii figured out, everything else is the same as it always has been. Find the area, apply the integral from, we're starting at y equals 0, ending at y equals 1. Do everything else we've done before. So the area of this thing is going to be pi times 1 plus y to the 3rd power squared minus pi times 1 plus y to the 1/2 power squared. Once again, be careful with your algebra. I'm going to get 1 plus 2y to the 3rd plus y to the 2/3 minus pi times 1 plus 2y to the 1/2 plus y to the 1st. Y to the 1/2 squared is just y to the 1st. I'm distributing a negative pi through the second one, so be careful of that the sign has changed. So I'm going to get area is equal to pi plus 2 pi y to the third plus pi y to the 2/3 minus pi minus 2 pi y to the half minus pi y. Once again, pi minus pi, we get constants canceling out. I don't have any common terms there. So what's left to do is just to evaluate that integral. So the volume is going to equal pi times the integral of, I'll just go in the order they're in. So I'm going to get 2y to the third plus y to the 2/3 minus 2y to the half minus y dy from 0 to 1. Getting kind of small in there, so we'll use a little more space here. Is everybody comfortable with where I got that from? Okay. So this is the answer. All I've got to do is evaluate this thing. So if I go ahead and get to that, 2y to the third makes 2y to the 4/3 divided by 4/3, which is times 3/4, plus y to the 5/3 divided by 5/3, so it's times 3/5, minus 2y to the 3/2 divided by 3/2, which is times 2/3, minus y squared over 2 from 0 to 1. As before, I want to reduce before I evaluate, so the 2 cancels the 4 down to a 2. Beyond that, nothing cancels, right? So my best structure here is 3y to the 4/3 over 2 plus 3y to the 5/3 over 5 minus 4y to the 3/2 over 3 minus y to the 2nd over 2. If I put 1 in, I just get all those fractions. If I put 0 in, I get 0. So altogether, I'm going to get pi times 3/2 plus 3/5 minus 4/3 minus a half. And then the common denominator of all that will be 30. So times 15, so 45, times 6, so plus 18, times 10, so minus 40, times 15, so minus 15. 63 minus 55 is 8. And 8 pi over 30 reduces to 4 pi over 15. So draw the picture correctly. Length from axis rotation to x or y axis, the x or y axis to the curve, and the radius from the axis to the curve. Those 3 segments every time are going to establish the radius structure. So I'm going to expect to see something like that on your paper each time. The relationship between the axis to axis, axis to curve, and radius. They're going to be related in some way, shape, or form. Each time you figure out that relationship, you get the correct radii, get the correct area form, you get the correct volume.